Sam, thanks very much for the invitation, and it's a real pleasure to come back and maybe have a more intimate discussion with the ability to ask as many questions as you want, and for us to provide whatever answers we can provide given some of the work that we've been doing in the context of that paper, but also in the context of other activities we've been pursuing. So I'm accompanied by my two partners in crime here, together, as I'll mention, with a whole bunch of students at Stanford. So as you introduce them, Tom Rindfleisch and Don Jackson. So if you don't mind, I'll just sit and just sort of go through this whole thing. So just a few remarks. So the work in that Journal of the Aeroacoustical Society that I'll discuss in a moment, it's a result of about 5 to 6 years of work from the entire team. And the three of us are here sort of representing the team, but there have been a number of graduates and undergraduates at Stanford who at different points in time and in their careers have helped with various different elements of what went into the actual paper we'll discuss, but also various other activities. So the reason you asked us about is the paper you see in the right, and there are links in the presentation that you already have, so you don't have to read anything there, but it's a paper that we worked on, as a result of all those years of work, but also we put together over the last 12 months and published in the Journal of the Aeroacoustical Society of America, JASA, in March 2024. That's when the report came out. I think that was the reason you guys invited us to the San Francisco ORSFO Roundtable meeting. So I have to say this is a highly respected peer-reviewed journal, meaning when you actually submit something to this, it goes to a very thorough review by a number of independent reviewers who we don't know who they are. They suggest things that we should explain better. They suggest changes or they ask questions. And in the process of peer review, you address all those questions before the journal paper is finally published. So it's a high bar. In addition, our research is funded by the FAA Ascent Center of Excellence under what's called Project 53. Which is very focused on assessing the noise prediction accuracy of the noise models inside FAA's AEDT. And as Sam said, AEDT is the Aviation Environmental Design Tool, which is effectively an analysis tool that allows you to virtually create airports, air traffic routes, individual aircraft, and you can see their performance, but also their noise, their emissions, and various other things that are important for the evaluation of the performance of the aviation system. While the FAA does fund our work, I want to make sure that everybody understands that the comments in this presentation do not represent, the FAA views or opinions. These are the opinions of the research team that actually put this work together. And by the way, as I go along, please interrupt me at any point in time. I'm going to tell you what we thought will be a good idea to cover in this presentation and what the objectives are, but we're here for you. So, and anybody else who is online, we want you to get whatever information we can provide from this presentation. So our goals for this presentation is to summarize the results of this paper. JASA, again, is a Journal of the Aeroacoustical Society of America. And we're trying to do it in as understandable way as we possibly can. This is not rocket science. It's actually relatively simple, but there's some nuances that you may have questions about. So please do interrupt. Because you're interested in topics of noise, in addition to the work we did in the study, we've been doing work for 5 or 6 years, and we have a number of observations that we thought might be useful to you, and we'll share them for whatever they're worth. And if there's further interest, just let us know and we'll answer more questions. But at the end of the presentation, we'd like to leave you with what we think this results, this study and the work that we've done actually mean to you, the members of the Roundtable Technical Working Group, both in the short term and the long term. And of course, again, answering the questions you may have that we can answer. If we don't have the answer, or we don't believe that the research we've done can answer your question, we'll tell you straight as well. Okay, so, I think you know this, but I did want to start this presentation by just sort of discussing that predicting noise impacts. Noise itself is hard to predict, but the impacts of noise are even harder. So just a few pictures, and I know it's a little dark here, but you can see there the entire Bay Area with a number of different airports that you see listed there, with 3 major international airports in the Bay Area, a number of waypoints, that are sort of like little breadcrumbs along the path of aircraft that we follow. On a 24-hour period, that's how all the trajectories of every aircraft that operates in a 200-mile radius of the Bay Area look like, and those are colored by altitude. So the colors, so I go here, that are a little redder are the lower altitude. So obviously, sort of the approaches and departures from SFO are all of these flights that you see around there. So it's quite a mess, right? And all these aircraft are overflying everywhere. And it's not just a one point in time thing. As you all know, it's a time dependent thing. So this is an animation of all those flies over 24 hours showing just 1 hour, in every sort of thing there. And you can see, it's hard to see here, but you can see how there's just a lot of stuff going on, right? Of course, we measure the noise and we measure the impact of noise using what we call metrics. And DNL, the dynamic levels that everybody's familiar with, is one way to do it. But you can measure the noise and the impacts in many different metrics. So the counts of how many aircraft fly above a certain area could be a different metric. And yet another metric will be the number of events above a certain DNL level. So, and above 60 and above 55 and above 65, whatever you want. So all these pictures, as I go back and forth, they all look different. So that means that we measure the noise and the impacts in ways that are subject to interpretation. Let's just be very direct about that. Right? So why did we do that study that we published in March? And why did we spend 5 or 6 years actually working on developing the infrastructure, collecting the data, analyzing the data, and actually trying to present it in a meaningful way? We are citizens of the Bay Area. We benefit from air traffic, but we also are impacted by noise from air traffic. So we want to improve the situation. This is where we come from. And we believe that when it comes to noise, having better prediction of noise under existing circumstances, but also hypothetical future circumstances, leads to better noise decisions. Whether it's route changes, noise impacts, noise distribution, so on and so forth, it is important that we have the best information available in order to understand how we might improve situations. So, of course, you mentioned, Sam, and I think it's common knowledge for everybody here, that all regulatory, noise impact filings and actions require AEDT analysis, and not just the AEDT analysis, but a very specific type of AEDT analysis. So prior to starting the work that led to this paper, we have been asking ourselves various different questions, and we have been talking to the FAA Office of Environment and Energy, and the former chief scientist, he's no longer there, had actually come to visit us at Stanford in 2019 and had said that, they were wondering if the accuracy of some of these noise models in AEDT was sufficient, particularly for areas away from the airport. Maybe less interesting to you, but that's how the study was generated. And they were interested in characterizing how accurate these models were, particularly away from the airport, but also understanding if it was not accurate enough, what were the sources of the inaccuracies? So presumably in the future, these models could be improved. So that's the generation of this whole study. You can read the paper and you may sort of think that it's too much detail or too much information, but it's all there. I'm going to give you the high level summary. And again, please ask questions. How do we go about generating the results that actually appear in that study? And it's very high level. So effectively, we look at the traffic in any one day, and as you'll see later on, over a period of 12 months, so an entire year, and we collect information about where every airplane is, how it flies in and out of the airports, what type of airplane it is, how fast it's going, how high it's going, latitude, longitude, blah, 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 blah. And we feed it to AEDT. I took a picture of the manual of AEDT so you can sort of associate with it, in order to understand what the airplanes would do. So if the airplanes flew exactly the way the airplanes fly in and out of various different airports in the Bay Area, what noise would they produce? Right? The advantage, well, let me just give you a little diagram, right? So you may have an observer down here, you have a flight path, which is generally curved, but if you focus, you see an airplane flying. So that airplane actually flies along the flight path at some speed, at some latitude, longitude, and altitude. And as it flies past one of these observer locations, it produces noise. And as you know, the noise starts very low, grows higher and then grows lower again as that aircraft passes by that observer location. So with the methodology we've developed based on AEDT, we can predict the noise at any observer location, any microphone location, let's say, from any aircraft flying around the Bay Area. But importantly, we also have a number of different microphones that we've deployed from our team and that Bert's team from SFO has graciously shared with us, where we can actually measure the noise. So not only we can predict the noise with AEDT, but we can measure the noise by putting a microphone, and then we can compare one to the other. And in the perfect world, the prediction from AEDT will exactly match the actual measurement from the microphone. Of course, that's a very tall order, right? So we do correlate our flights with the ground sound peaks. We are very careful. I won't go into the details here, but if you want to know more, Tom is probably the person to discuss this. We go through all the noise recordings from the microphones and correlate them with whether there was an aircraft flying around or not. If we see that there's multiple peaks, if we see that's noise that may have been generated not by an airplane, but by a truck going by, or a jackhammer doing construction close to the microphone, we throw all that data away. So we only keep data from overflights over an entire year, as you'll see in a moment, that we are fully convinced are actual aircraft flying above. And how can we do this? Well, we have the timestamp microphone recording, and we have the timestamp flight trajectory, so we can tell if the peak of noise happens to be when an aircraft was at the minimum distance to the microphone. So we have various different things that we do. We go much deeper than that simple explanation, but we are very convinced that the data we've collected is great. The data we keep from the data we collect is guaranteed to be resulting from aircraft events or noise events. So we run AEDT, we predict the sound, and then we do comparisons. This is what's normally done, right? So we've done this for every flight into SFO. So let me be very careful. The study focuses on arrivals into SFO. We are pursuing the effort to do departures as well, and that will come later, probably early next year. But it is about 200,000 noise events over that course of a year at multiple locations. But today we're going to focus on a microphone location that actually is one of the San Francisco airport microphones in Foster City. We figure we are here in Foster City, so we'll tell you about that. The difference between what we've done and every other study we have seen published over the last 5 to 10 years is that most of the noise studies that are published, they have anywhere between, I say 10 to 30, but sometimes 5 flights, to 30 flights or something. This is 200,000 flights. So statistically, the results are very meaningful, I would say. And we've taken great care to ensure that those statistical results are very meaningful. So the particular microphone we'll be looking at is the SFO NNT12. So noise monitoring, what's a T for? Terminal, yes. So noise monitoring terminal. So it's roughly in that location. So once we compute all of the trajectories and the noise from all these aircraft, and once we've ingested all of the microphone data, we can start looking at that database in any way we want. We can say, look at 737 aircraft or Embraer's 175, look at things in the winter, look at things in the summer, look at things when the temperature is higher than X, et cetera, et cetera. So the ability of putting all of this into a huge database, which by the way, Don, as a tremendous software developer, has been mainly responsible for, it's what allows us to look at the data in any way we want. And we looked at it in ways that make sense to us. But if you wanted to look at the data in a slightly different way, we could query the database and sort of produce these types of results. As I mentioned before, AEDT can be run in different modes. And one in particular is the one that gets used for all kinds of regulatory type of studies, right? So we will call that AEDT-R for regulatory. We've also tried, in collaboration with both FAA and the Volpe Center, to use AEDT in what will be the most accurate way that these folks who've developed this software would actually, sort of think the tool should be used. So we've done all that, and then we've analyzed all kinds of statistics. We are engineers and research scientists, and we love data. So we probably look much more data than you would ever want to look at, but we have all of that, and some of it has actually been put into our paper. And then we are trying to identify how good the predictions are and to a certain extent, although it's not always possible, understand when the predictions are not perfect, why they're not as close as possible. Okay, so here's the punchline for the study that we actually put together. So we've taken some selected results, one plot from that paper, so you can actually see what happens. So we're going to be focusing on ADT AE, which takes into account altitude and airspeed controls. So this is presumably the best way you could use ADT to get the most accurate results, not necessarily the regulatory thing, although the paper has results for that too. We're looking at this one Foster City microphone location, and we're looking at all the aircraft flying over or nearby that microphone location and landing at runway 28 left in San Francisco. There's a lot to unpack here. So this is the difference in decibels between the predictions from ADT and the measurements from the microphones. So in a perfect world, the difference between the microphone measurement and the prediction for ADT should be 0, right? So that's perfect prediction. So 0 is down here, or up here, I should say. In the horizontal axis, we have the most typical aircraft types that land in San Francisco Airport, from 747-400s all the way to Airbus A320s and Embraer's 175, so on and so forth. And for each class of those airplanes, in the 200,000 flights, we have, you know, anywhere between the low 500s to the thousands of flights, essentially, right? And what we do is for every one of those flights, we compare the measurement to the prediction, and on average, we say what's the difference. So we do this for 2 different noise metrics. Is everybody familiar with LA Max and SEL? So there's 2 different ways of measuring the noise, but let's focus on the LA Max, which is the maximum noise in any one noise event. What you end up seeing is that the numbers are sort of given by the what we call this, the green diamonds, right? So the 747-400s, pretty well predicted. They're almost on the money. But every other aircraft type that commonly comes into SFO is under predicted. So you see negative numbers by 2 dB for the 767-300 TRs, all the way down to, you know, some aircraft that are predicted by minus 3.5 dB or so. So again, this is 200,000 flights now sliced by the type of aircraft. So a very representative sample over all months of the year, right? Over all different weights of the aircraft, variations in the final approach, although this microphone is very close to final approach. So the altitudes are pretty close to 1,700 feet of altitude, and the paths are pretty well concentrated over the sort of the final approach to 28 left. So, but in general, we see that although there are a couple some airplanes that are well predicted, the vast majority are under predicted by anywhere between 0.1 or 2 and 4 dB.
If I may ask
Yeah,
you a
please.
question, for those who don't really know what that translate in real life.
Yeah.
If the underpredicted by 2 dBs, what is that? Is that just a small percentage, or is that really goes to
great
double?
question.
What is that?
Great question. The decibel scale is a logarithmic scale that measures the amount of noise energy that we hear or reaches our observers. If you had 2 identical airplanes and you measure the noise and you took one airplane away, the noise measure will go down by 3 dB. So when you take 1/2 of the acoustic energy, so instead of 2 airplanes simultaneously, 1 airplane, that brings down the decibel level by 3 dB. That's the mathematical description of that. So of course, the human ear perceives noise in a very nonlinear way too, right? So we have a very long range from, almost 10 to 20 dB, depending on how young you are. Not most of us, I would imagine, to about 100 to 120 dB, which is close to the threshold of pain and where you can cause serious damage to your ears. So, but 3 dB is effectively taking 1/2 of the total energy radiated by noise.
Thank you.
Yeah. So, you can look at all of that. We did look at the individual types of airplanes just to show it, but also at the average weighted by how many airplanes we see, because we see a lot more Embraer 175s than we see 747-400s in approaches. And on average, if you look at the LA max metric, we underpredict by about 2.75 dB, again, on approaches to SFO. We don't want to extrapolate our results beyond their limit of applicability, all right? In the SEL metric, because it's an average metric, it's a little bit better. So it's we underpredict by about 2.5 dBs.
So when you say we underpredict the
ADT underpredicts, I should say.
okay, so it's underpredicting and the actual noise that we're perceiving and we're hearing on the ground is higher.
Correct, correct. So yes, if you hear an airplane going by, and you measure it with a microphone, there'll be an amount of dBs. On average, when ADT predicts that same airplane flying over the same microphone location, it will predict a noise at the microphone that is about 2.5 to 2.75 dB lower, right?
Could you back up a minute in terms of the comparison or the illustration of the impact of the 2.5 to 2.75 to the layperson? What does that mean? Is that like a lawnmower? It's not a lawnmower.
Actually, let me go up a little bit to a plot that I'll show you, and then I'll come back to it.
Okay.
You know, noise perception is subjective. So, you know, a 15-year-old may predict the same noise event differently than a 55-year-old.
Yeah.
And somebody who's more sensitive to being woken up at night or, you know, disturbed in terms of learning during the day. So everybody is different. But in general, people do studies of the impact of aviation noise on people. And you're probably familiar with some of these curves. And if you have not seen this, at the moment, all regulation is based on what we call the Schultz curve and the Schultz-Ficon curve, I guess, which has this green and yellow curves. This says for a given noise level, which you see in the horizontal axis, let's say 65 dB, what percentage of the population will be annoyed? Highly subjective. So how do they do this? They actually subject people to various different levels of noise, and they ask them, were you annoyed?
Yeah.
How annoyed? Very annoyed, highly annoyed, you know, not annoyed at all, et cetera, et cetera. So by looking at cohorts of population, so the young people, the old people, the more noise sensitive, the less noise sensitive, you come up with an average human being and how they respond to the noise. So in 1970 or thereabouts, right, the Schultz curve, I think we were a society that was much more tolerant to noise. So with 65 dB DNL, only about 10% of the population was annoyed. If you look at further studies in the 90s, early 2000s, or even the latest FAA NES study, which is the National Environmental Survey, which is still, I think, being finalized and looked at, what you see is that that curve's moved to the left. So, for example, if you wanted to have 10% of people annoyed in 1970, which would have been a 65 dB DNL, with the latest NES study, that suggests that the level of noise that is going to annoy that many people is closer to 45 to 50 dB, right? So, again, that study is not completed. So what does it mean? If you were to say, instead of 65 dB, you have 3 more dB, 68, well, you'll see that in the old time, it almost doubled the number of people who are highly annoyed. In the new times, maybe even more.
Even more so.
So it's significant, although of course noise is affected by many parameters. It's, the aircraft flies, we don't know if the aircraft has extra fuel for the next flight or not when it lands on SFO. It's hard to tell whether the flaps and the slats and landing gears and various other things are deployed. So there's variability, which I'll come back to in a moment, but it's 3 dB is not a small number.
Okay, that's, yeah, thank you.
In my opinion. Let me go back to this graph. The other thing that we wanted to show you is that in ADT, aircraft that is flown assumes a particular aircraft weight and fuel, and therefore, every time it flies the same trajectory over a microphone, it produces the same noise. Very deterministic, we call it. In reality, airplanes fly at different weights, different weather conditions. The wind and the temperature gradients and density gradients in the atmosphere disturb things. So
And different pilots.
different pilots fly the airplanes differently. Very good. So what we actually see is that while the average noise for each class of aircraft is what you see in there, there's a lot of variability. Sometimes 2 more dB, sometimes 2 fewer dB, right? But on average, the difference between the prediction and the measurement is that high. So let me keep going a little bit, and you guys jump in. So I want to summarize what we saw after doing all of these things. And again, it's a very compressed summary, but we did see that for both LA max, the maximum noise of the average peak event, and the SEL, so this is an integrated noise type of metric, with the best way of computing the noise with AADT and with the regulatory way of computing the noise, we saw consistent underprediction. So the tools that typically predict less noise than what the microphones measure, right? Again, the study was focused on arrivals to SFL, right? So we are going to do departures. So I don't want you to extrapolate to departures for some of the cities and municipalities that are, around SFO that are probably more concerned about departures than arrivals. Right? We also found, because we have so many data points, we can plot it in various different ways, that the noise model in AADT does not predict the proper variation of noise with speed of the aircraft. You're probably familiar with a car going by. If a car goes by, forget about the engine noise, just the aerodynamic noise. If it goes by at 20 miles an hour versus it goes by 100 miles an hour, the noise is significantly higher when the car goes by at high speed. The same is true of airplanes. The faster they fly, particularly on arrivals, the more noise is actually produced. The ADT noise model was created for a time where the engines were, much noisier. The area of concern was much closer to the airport, and they were not concerned about what's called the airframe noise. So there's a fundamental issue in the physics of that particular model. By the way, nothing against the modelers that created that noise model. At the time, they were focused on very specific type of airplane engine combinations and very specific types of operations close to the airport, right? So, and that's what they developed a model for. The issues are now that the airplanes are quite different, the engines are quite different, and the airframe noise in approach in particular is a significant source of noise. This is, I won't go into the details here. So we fly the airplanes exactly. So we fly. ADT flies the airplanes for us exactly or as close as possible to the actual altitude and airspeed that we saw that airplane actually flew. In the regulatory mode, people normally use standard profiles, which are roughly representative of what's going on, but not very close to the actual sort of profiles flown. We believe we need better noise modeling fidelity, right? And that means a lot of things. To put a new noise model together requires that we estimate the weight of the aircraft better, the wind and weather conditions, which we take into account, but we and ADT will have to do it better. But that will lead to better decision making and more informed decisions, I would say. And the potential solutions are improving the models in noise and ADT, obviously, but also an understanding that the noise models have a certain margin of error. And if things have a certain margin of error, you should take into account that error in the predictions, when you set up rules for various different sort of procedure changes, etc.
So
That's our opinion.
I'm not sure if I'm even gonna ask this question right.
Doesn't matter.
Because you feel that AEDT is not taking into the account the actual the speed,
Yeah.
is that part of the reason that they're under reporting the noise by that 2.5%, 3%?
It's one of the contributing factors for sure, yes.
Okay.
Because if there's any variation.
It's not on top of that 2.5 to 3%.
No, that's the 2.5 dB is the total. And now you could say part of it is because ADT may think the airplane is a little bit lighter, has less fuel than it really has. Heavier airplanes make more noise, right?
Okay,
Part of it is because it doesn't.
I just want to make sure it wasn't a compound.
No, it's not
Okay,
compounded.
thank you.
The numbers of 2.5 or 2.75 dB on average that we talked about were the total amount of underprediction.
That's a great question. It's not 2 or 3%, it's 2 or 3
dB,
which is
I'm sorry.
50%.
Yeah.
Right. I'm sorry,
Yeah.
terminology.
But other than that,
Lots
exactly the great question.
Sorry?
A lot of compounding in there.
Yes, yeah, there's a lot of
So-
stuff in it, but that's the total amount.
So let me make sure I understand that.
Yeah.
So the 2.5 or 3 dBs.
Yeah.
Well, not a percent. You said it's half again? the
It's half
impact
of the acoustic
Of
energy.
the acoustic energy. It's not like an earthquake that every 1 degree is like 10 times higher, is it? Or is it?
It is,
It
the
is.
only thing is that
Okay,
when your ear hears 10 times the acoustic energy, it does not perceive it 10 times as loud. So it's, your ear kind of filters that noise. So, typically you want to say how many dB
Well,
a human being thinks it's twice as loud. So yeah.
It also depends on what the ambient or the average level is.
Right.
So if you're in an area that's got 50 decibels, normal DNL, and you cut the traffic in half, that's going to bring that down by 3 dB. So it's 3 out of 50. If you're at a lower level, quiet night, and you change the traffic by a factor of 2, that's adding 3 dB.
2 versus.
And so that's why, measuring or estimating the effect of noise is different and very difficult, very subjective.
Depends on where you live, is what you're saying, right? If you live in a super quiet area, then, a number of events of noise may subjectively sort of make you be more annoyed and have more impact. If you live in an area where there are trucks going by constantly, you may not even hear the airplanes, right? So.
I don't want to detract from this, but you made a comment earlier, I didn't fully
Of
understand.
course, go ahead.
You said the variations between the model and the actuality varied with the type of engine or type of plane.
Yeah.
Why so help me understand what that,
Oh, because ADT, inside ADT for each airplane and engine combination has a different effect. A
and the
slightly
model
different
assumes
noise
it's
model.
all the same.
Sorry?
So are you saying the model assumes they're all the same?
No, they have different ones, which
They
come
do.
from certification data from the manufacturers. But some are better, some are worse, to be completely direct. So.
But the variation for each model would be, the differential is about the same per model, even though
Well,
Prediction
no, I
may
mean,
be
if you look
different
at all
from
the
mine.
airplanes, there's some airplanes that, have, let's look at these.
He's asking about.
Oh, I see. You mean the variability?
yeah,
Yeah, when we measure the noise from all 737-800s, let's say, there's a mean or an average value of the noise, but sometimes the wind blows in this direction or that direction. There's about, most airplanes have a variability of about 2 dB. I don't think it's exactly the same.
No, it varies, but
varies
it's in that order.
It's
I guess my question was, if I have a plane that has a DB, say 50.
Yeah.
And the differential, what we might find might be 53. Where if I have an engine or plane that has a DB of 60,
Yeah.
the variation is still 3, it's still 63. It's just that you can factor that in. That's a solvable issue.
So that's the difference between the prediction
Yep.
and what we measure.
Gotcha, okay.
And every time a pilot flies exactly the same, a different pilot flies exactly the same aircraft,
On a
and you
different
have
day.
different weather and so on, you're gonna get a different result at
Slightly.
the noise monitor. And so that is taken into account here. that
Gotcha.
It does not reproduce on an exact basis.
Gotcha.
So sometimes if the prediction is 3 dB under the real noise on average, sometimes it may only be 1 dB because, that pilot flies the airplane more quietly, let's say. Sometimes it may be 3 + 2, 5 dB difference because that aircraft was flown in a very noisy way.
Yeah.
Now, when you talk about the noise level produced, and this is on landing.
Yeah.
So are we taking into account the speed breaks noise that people are hearing?
So the
Which
models,
depends on how they're flying a route.
the models do not take into account in detail,
What they were doing.
Yes, because when we see the airplane flying around, we know what type of airplane it is. We know its license plate essentially. We know the engine that it has. We know its altitude and speed, but we cannot tell in
What they're
general
doing.
what the pilot is essentially doing. If we knew that, we would be able to do better predictions.
So we should say again, that depends on where in the flight
Right.
profile you are. So coming in for a landing.
Right.
You can almost guarantee that the landing gear are out, the flaps are out, all of the hardware is out.
So
Coming over the side-by waypoint, which is the other place that we measured, it's a transition point between a sort of cruise flight and coming into air traffic control. And different pilots will deploy the hardware at different times, and it makes a substantial difference difference. There, sometimes the difference is up to 6-7 dB.
Yeah, much more.
Well, I know that when on one of the reporting tools that has been around for a while for reporting airport noise, you know, one of the questions they ask in the little thing about how
Yeah.
noisy was it and how annoying it was, you know, did you hear speed brakes? Because it's a different.
Yeah.
Yes,
different
it's a
pitch
different
noise and
pitch
you can-
noise.
yeah.
So I know that that's one of the questions they asked, but you weren't taking that specifically into account, but it would be registered in the actual noise event.
Correct.
In the sound monitor.
Yeah.
AEDT does not know that.
Mhm.
And in fact, we had a colleague at NASA Ames who flew the same type aircraft and noticed that the pilot deployed slats at different points over our noise monitor. And we were actually able to measure both of those sound peaks, and the difference was like 6 decibels.
She was in
Yeah.
Southwest, right, flying the exact
No,
same. And he had two 737s identical, one flight, the pilot deployed the flaps and the slats earlier, and one flight much later.
Okay, thank you.
Yeah, I did not appreciate that pilots can make that much of a difference in the noise,
Yeah.
6 to 7 dBs.
It's
That's
incredible.
the airframe
Yeah.
noise we were
Yeah,
talking
I
about.
fly
might
this
add-
under side-by,
Yeah.
and I can watch exactly the same type of aircraft go over, and sometimes it's nice and quiet, and sometimes it is loud as all get out.
If I might add, the aircraft automation, the FMC, flight management computer.
Mhm.
If the pilot's going hands-off and letting the computer fly, it can do the same thing.
Yeah.
And it will do it in different places. You can run one flight after another behind each other. And those FMCs will do it in different places.
The automated system will do differently for different, at
Why,
different
why
times.
would that be? How do you explain that?
The wind speed, it varies.
But not the flaps
No, the flaps will come out on a schedule,
typically.
but.
Throttle changes. and
throttle
engine
changes,
and
speed
things,
breaks,
slips,
things
those
like
sort of
that.
things, yeah.
All those things contribute to
Mhm.
noise on the ground.
Yeah.
So when I do noise 101, I tell
Yeah.
people, okay, if you're riding in an airplane, when you hear the landing gear come down, ka-thunk, zzz, those noises, when you hear the rumble,
Yeah.
translate to the ground.
Yeah. So how the airplane is flown
Mhm.
matters to what's the
Yeah,
noise that's.
but we should be clear that the flaps and the speed brakes are all are manual operation by the pilot.
Right.
That's
The
not
pilot
automated
decides
by any
typically.
means. And it's not as if some pilot is better than another pilot necessarily, because the weight of the airplane largely controls the amount of flaps you need to keep the airplane in the sky.
Also the traffic around and the workload in
And
the
the
cockpit and
instructions
various
from
other
air
things.
traffic
And if the flight
To
is
slow
late,
down.
then the
So,
pilot's.
so the
trying to make up.
airspeed and the weight of the airplane are critical
Yeah.
factors of when the flaps come
Yeah.
down. And ATC can tell you to slow down, and you're gonna need your speed brakes to do that, depending on circumstances.
I'm being mindful of time, and I know that we are now going over time, so.
You
You're
trump.
fine.
I know you guys have another presentation, so I can jump to conclusions, or I can share some additional information beyond the study that I thought or we thought could be interesting.
Actually, I would appreciate it if you share as much
Completely,
as you
okay.
can.
I'll
What we have at the next item, we could handle if we have the time. If not, we could defer. to the
Okay,
next meeting.
Yeah, no, this
We
is
would
really
like to use our
interesting.
time with you.
You're the boss.
Appreciative of this.
Appreciate
Okay, so that paper has tons of results. We're happy to go through anything, but we've given you sort of the overall picture. We've also been collecting data now for a good 6 years, right? So beyond the study, we've been looking at what's happening, and one natural experiment that happened in terms of noise was COVID.
Was what?
So COVID, the COVID pandemic.
Okay.
If you look, and sorry, this is a bit small and it seems smaller there. This is in time from January 2020, so right before the pandemic, all the way through March 2020, and you see a precipitous drop.
March
in-
17th.
March 17th was the date. Right? So when traffic went from, let's call this 100% to about 20% in various different airports. It's colored by airport. You have the slide so you can look at it in a little bit more detail, but blue here is SFO. So SFO went from what, about 1,200 operations per day or so to to probably 250, right? And the trough in there. So, and it's been recovering over time. And I think it's just this year that you come back to the pre-pandemic levels essentially, right? Or almost.
1150 the other day.
Yeah, 1150. So getting close to that level. But you have other airports like Oakland and San Jose, et cetera, et cetera. And actually Oakland recovered more quickly because we were all ordering on Amazon and we weren't going to the store. And there were a lot of airplanes bringing stuff, a lot of cargo, right? So, but the interesting thing is that those color bars are the traffic over time with this sudden drop, right? The blue line is the number of complaints about noise that actually are reported to the stopjetnoise.org.
Stopjet noise that Adam Worrell
Yeah.
put together.
So he didn't want to share with us the data about the specific locations of where the noise complaints were, which will be very useful. But he did share the aggregate number of complaints. And, it's scaled, the blue line is in complaints per day. So at a top level of about 7,000 in this app to the bottom level here of about 2,000. So one of the things that we noticed in this data, and again, it was a very natural experiment, right? We don't normally get to say, hey, you know what, Bert, tomorrow, half the number of airplanes that come in, so we can actually make some noise measurements and how many people complain about these things. So, but what we noticed is that when you halve the number of flights, typically you get to about half the number of complaints. But when you halve the number of flights, you're only reducing the DNL level roughly by about 3 dB. So one of the things we wanted to tell you, because you had some questions that you had sent that we will try to address later on, is that DNL was the metric that was chosen a long time ago to measure, impacts of noise. I said measuring noise is hard, but impacts of noise is even harder. We really strongly believe, and it's not just us, there's some colleagues at MIT that are doing similar studies that think the same, that a better measure of annoyance is a combination of amplitude of noise metrics and number of times that individuals are overflown. The DNL metric doesn't make it a distinction between one very loud noise event and 100 slightly quieter noise events, but you'll be probably much more annoyed at about 100 of these events happening at a slightly lower loudness level.
So from an
yeah.
intuitive point of view, DNL measures the average over 24 hours of the noise energy that is per second falling on an observer or a microphone.
With a penalty at that.
Yeah, the number that are reported by stopjet noise is an event-based measurement. When a plane goes over and interrupts your patio conversation, that button gets hit. And so it is an actual measurement of when an annoyance happened and the number of them during the day or during, whatever time period that you want.
And let me admit, as a scientist, of course, it's a self-selected population that reports these noise events. So they're not representative of the full population. So we understand all these details. So take these conclusions with a grain of salt. But
And these people would have been at home more too,
it's possible they're at home. Yeah.
because of the COVID,
Yeah.
During COVID,
impacts.
yes.
People were home and noticing it.
But others on the stopjet have done it mobile.
Yeah.
So we'll find them all over the Bay Area, but they report from home, even though they were elsewhere. The other one too, is we have some working from home typically that will hear an aircraft and they'll sit there and go, I hate this airplane, I hate this airplane, I hate this. Did you remove those, the multiples on a single within a certain amount of time?
I think Adam removes the multiples on a single. You're only.
In these data, we do not.
We do not.
Because
Okay, I
we
see.
don't have that level of detail. So
okay.
that's why this can't be used quantitatively in the sense of making a dose response curve.
Okay,
But
that's
the
what I was curious.
observed rate of complaints is accurate here.
But I thought Adam did not allow more than one complaint per noise event because he gets the aircraft type.
He does
Well,
filtering
per person.
Per person.
Well, when I
Then he gives them that
use that
response.
app and I hit the button
Yeah.
and it says could not determine, no flight or could not determine, it's like, but it's like,
You may have done
it
it too
does.
late after the event, maybe.
Well, no, I mean, I'm still here, it's takeoff noise, and yeah, I'm still
Okay.
hearing it, it's still
Okay.
overhead.
Yeah.
And it will not let me
Yeah.
select it, it doesn't report. It stops for
Right.
30 seconds or a
you
minute
can report.
before it'll let you
Mhm.
hit the button again.
Yeah.
He's trying to find the aircraft in real time.
Right.
When we do the comparison, we do it after the fact. We have the actual track
Yeah.
and we have the measurement of when it happened on the noise monitor. And we can measure that to within a quarter of a second.
Right.
To be damn sure that it's that aircraft that made that.
Yeah,
that
but we don't
sound.
deal with the compliance, right?
Anyway,
Our point with this slide, which is not a result of our journal paper, but of our observations over the last 6 years, is that we strongly, as a team, believe, and if I'm misspeaking, please say something. We strongly believe that DNL is not the best way of measuring impacts of noise and annoyance of noise. We do believe that a hybrid metric of some kind that mixes DNL with a number of times that you're overflown, particularly a certain level, is a much more relevant metric to use for noise annoyance of overflown communities.
Yeah, and I personally agree with you, but not only just me, I think this has been the conversation that we have been having in the roundtable from us, members and members of the public who are really impacted by the noise, and we hear from them often that this current modeling at DNL is really not reflection of what the actual noise people are perceiving and
Right.
dealing with on the ground.
It was a good metric when it was created a long time ago, based on the society we had at the time, the airplanes and the engines we had at the time, the concerns about noise we had at the time.
Mhm.
I think over the last 50 years, 55 years now almost, these studies were done probably in the 60s, so maybe even 60 years, things have changed a lot. So we need to, if we are trying to come up with a logical way of measuring impact with a metric, we probably need to think more broadly about the types of metrics that are. And this is easier for researchers to say. It has monumental implications at the level of communities, airports, the FAA, the federal government, and local government, et cetera, et cetera. We realize that fully. But if you want to have a better correlation between a metric and annoyance or impacts, you're going to have to do better than that.
So,
Yeah.
again, I don't want to get ahead of where you're going on this, but what's been the criticism of your study? What's been the feedback to those who say?
I think I'll say it, we've gone through a lot of review, not just the peer review, but internally with our colleagues at the FAA and everything else. Well, first of all, there's one airport
Sat in on our group meetings.
every week, right? So every other week. I think the main thing is it's one study. It does have 200,000 flights, so that nobody can argue with. It's far and above bigger than anything else that's been done before. But it's at one airport, right? We're overflying water, we're close to water, there's reflections, there's different ways. So I think the FAA believes ADT will do better at other airports. And I think that will have to be studied, and we have a little note or recommendation on that. And also, so far, we've only done the study for arrivals. So there is also a prediction by the FAA that in departures, the ADT's noise models are going to do better because the noise is dominated by the engine noise and takeoff. And the engine noise was kind of the fundamental thing they were trying to get in the noise models in ADT. So we're going to do the departure part this year. We don't have the resources to try 3 different airports. The FAA may want to do that at some point, I imagine.
So I think the departure noise is going to be interesting to see how that correlates to the data you found here. Because so much of the departures, they try to take off over water, but Brisbane and San Francisco has that jut of the peninsula in San Bernardino Mountain.
Right.
And it reflects noise
Right.
so much differently when a plane, I'm out at our yacht club that's on the water right off the shore of SFO.
Right.
And you hear the planes going by and they're annoying.
Yeah.
But in Brisbane, because we're on a very steep hillside and there's planes trying to get over and make a turn around that mountain on the takeoffs, they come between the bowl of our mountain and where our town sits, and the noise just
Reverberates a bit
ricochets.
more, yeah, these are, by the way, physically very complex phenomena. It's hard
And
to
what's
model.
interesting is even in Brisbane, and our Facebook page will light up when there's one of those really horrendous flights. But people that are a third of the way up the hill of our little valley will hear it tremendously. And people on the flatlands that are, 100 feet lower in elevation are like, we didn't even hear it because it bounced. They got the initial
You know,
impact
the
of
way
the
I
noise.
normally explain that to people, noise is not exactly like light, but imagine light hitting a pool. And you see what are called acoustics, right? So sometimes the light gets deflected, so it adds up and it's really bright, and sometimes it's less bright. So with noise, or with acoustics, it's somewhat similar. Which
It'll be
means
interesting
there's
to
some
see with the
focus areas and
departures.
there's some defocus areas. So some places will hear higher noise, some places will hear noise.
Yeah, it'll be very interesting for us.
I would like to check with staff and Jean if they have any questions, and we'll come back.
Yeah.
Yeah.
We may even want to see if our public wants to weigh
Yeah,
in.
definitely, I will go to public, but after we're done with ours, Kathleen or Jean, if you have any, or staff, anybody really, that have any questions or comments, Jean?
Yeah, thanks, Sam. Actually, I don't. This has been a great presentation. Appreciate it. No questions at this time. Thank you.
Thank you, Jim.
Thank you. Kathleen, you good?
I'm good.
Okay, then back to us.
Can I make one comment?
Absolutely.
And this again, is just an observation of your presentation when you talk about you're measuring noise and the accuracy of it.
Yeah.
And you do so for the purpose of better decisions.
We hope.
And it's always been a pet gripe of mine that the word noise is sort of a defined term with respect to this. It covers a lot.
Right.
But there's an aspect of it that I think is becoming much more important. That's the health aspects of noise.
Right.
So when you talk about decisions, it's not a noise decisions.
It's an impact of
It's an
noise,
impact.
which can be health,
which
among
health
other
can be
things.
significant.
Childhood, lack
Yes,
of
yeah,
learning,
so-
maybe that you get annoyed and your
Yeah.
blood pressure goes up. There are people in public health who translate these noise levels and noise number of events into actual public health impacts. I can point you to studies, but I'm definitely not a
No,
specialist in
you're
that.
not covering that, but
I'm
I
an
would just say, when I look at this presentation, I was talking about,
Yeah.
it's not that I'm disturbed because my cocktail conversation's been.
Yes, understood.
Because I may have a child that
Understood.
has some sensibilities that this is really a
Understood.
problem. So
Yeah.
anyway, yeah,
Yeah, and so there are
Yeah.
many different impacts of noise
yeah,
and
so,
some are
and
much
so
more significant. than
what
others.
I'm hearing you saying, by the way, I'm
Mm-hmm.
hearing you're saying that the current modeling is not accurate in the sense of actuality. I mean, it's off by a couple of dBs.
It's up by
dB.
2.5 to 2.75 dB,
And
depending on
secondly,
average, right?
that's more critical today because our sensitivity to noise has changed.
Mhm.
So 2.5 or 3 dBs is different today than it was 30 years ago, or
I think that's a
55
fair
years.
assess, a fair
So
statement.
there's a double impact.
Yeah. I think
Has
that's a fair
the
statement.
FAA given you feedback on how they are planning to use this data?
The FAA has the Center of Excellence where many studies are done on many different topics, not noise only, right? I think the idea when the study was created was to understand whether ADT was good enough or not, and to understand, if not, what could be done to improve it. As a consequence of our project and our study, we are giving feedback to the FAA on everything we think that they could actually do. At the end of the day, it's up to them to decide what they want.
And you don't have any indication of how that is being received by the FAA?
I think they've been a great partner in sort of helping us come up with a study that has the highest possible quality. And frankly, that uses AEDT, a tool that they've sponsored and made the standard, that uses it in the best possible light, right? So we're trying to make sure we get the best results out of AEDT. So I think they're taking it all in and they're saying, okay, well, let's look at departures as well. And eventually they may want to look at different airports, right? But I do think that the sheer size of the data set that we put together is maybe the main contribution that we come up with. Maybe going from 10 airplanes or 10 flight studies that do that to 200,000, right? So.
And do you anticipate your departure study is going to take the same length of time?
Oh, we'd like to wrap it up in about a year or so.
Oh, okay.
So no.
Good, we
because-
won't be waiting 5 years.
Because of the 6 years, we spent a lot of time setting up the infrastructure, the
Right.
collection of data from the aircraft, the curation of the noise data, the automation of AEDT, because we can't sit down there and run 200,000 airplanes, by clicking on the
Right.
interface.
Okay,
So we spend a lot of time building the infrastructure, and now we can run, 12 months in about a week or so is what it took us to run 12 months of flight. 4 days, 3 days, something like that. So we can now run,
A lot
studies
quicker,
a lot.
yes.
quicker, yes.
The different aircraft are parsed out to different computers
Yeah.
in like a Google cluster
Cluster
or
cloud, yeah.
Amazon cluster.
Yeah.
And so you can multiply the number of computers.
We can run many flights simultaneously, so we do 200,000 or 250,000 flights in about 3 days.
How many computers you want to pay for?
Yeah, it's expensive. So
And
it's-
Mr. Collins, your question about what the FAA thinks, I think best people to answer that question is the FAA.
Okay, I was just asking in the group if they were incredulous of your.
I think that
data
they
or
in
not.
general take the information and then do their own thing, they don't give you any.
I have to say,
immediate feedback.
I've known the FAA for a long time. I took 3 years off from working at Stanford to work at NASA headquarters in 2006 to 2009. And in there at NASA, I was the partner of the FAA for many things. Since then, I served in their advisory committee or advisory council for the Office of Energy and Environment. And twice a year we meet to sort of give feedback to the FAA. And I make many of these comments at some of those meetings, so they understand some things, and we have internal discussions. right?
Sam, a couple more questions. This is one study, although it's extensive.
Yeah.
Are there other studies currently taking place elsewhere that are similar
So-
to this study?
FAA is funding a project that is similar that our colleagues at Georgia Tech have been pursuing, but with vastly lower amount of flights. But they're using SFO as well. In fact, you're sharing the data with them. It's a slightly different study in the sense that they actually have cockpit data from one of the airlines, so they know exactly what the pilot was doing. So they're looking at different things, and it's a much smaller number of flights. Right?
And I guess my purpose of the question is to try to figure out what will it take to get a change.
Yeah. So there've been
So-
studies, by the way, in Heathrow. There were studies in Tel Aviv that we cite in some of our papers.
Mhm.
So there have been a number of people doing studies that are typically much smaller, but what will it take? I think it's from, we are scientists and engineers. We want to put the best quality data out there, so it speaks for itself.
There are a few more like at Zurich
Yeah.
Airport, where they're trying to do larger scale studies. It's interesting looking historically, this has not been done before. People have sort of taken the predictions and done what they can with them. There are very few indications of any systematic, large volume study of the statistics of what AEDT and other tools are doing.
And again,
This is opening, I think, a new era of,
and again, the world has changed tremendously in the last 50 years, right? These noise models for, airplanes that were taking off and landing in 1970 from SFO would probably be significantly more accurate, or even if the inaccuracies were similar, the noise levels were so much higher that it mattered less, right? So,
Yeah, I think the study kind of really provide enough sufficient data to at least start thinking and looking at this model that currently using, how it really is not reflective to what is happening, and it needs to be either replaced or updated at least in a way that will be, especially, I mean, for us, it is so critical, I guess, because you're getting information and getting analysis
Right.
of a model that based on which policies and
Right.
procedures and routes are being established are not really actual noise impact that is being felt by the public. And
There's a
that
difference.
is really problematic for me as a policymaker, and I think it should be problematic to the FAA as well, that need to be relooked at this point. And I think, like you mentioned, your study just having that extensive 200,000 flights and the thoroughness that you have gone through the study and from every aspect. And as a casual observer, I mean, forget about me being on the roundtable, as a casual observer here in Foster City, I could tell you with full confidence, the speed of the plane coming into land makes huge difference. Sometimes we see these planes like almost hovering in the sky and you don't hear anything. They just like almost hovering, nothing, not moving. And then you see one zipping by and the noise is ridiculous, same plane. So many things. But I wanna kind of, for the interest of time, go to the public if no one else here still have any more questions. Let me go open it up to the public to see what the public
Perfect, yeah.
have, any
Yeah.
questions, hopefully.
Absolutely.
With that, let's go ahead and open for the public, Diane, and for those members of the public who would like to speak, Diane will tell you how to do so.
Yes, we have one member on Zoom that would like to speak, and two members now. First with Miss Darlene Yappi and then Mary Jo Fremont. And I will ask them to speak once I have the timer. Had technical issues earlier today, but
It's good.
2 minutes, right?
It's gonna.
Miss Yappi, if you wanna go ahead and get
I can time
started,
it with mine.
exactly,
Miss Yappi, you have 2 minutes.
Thank you for the presentation. 3 question areas. An HMMH observation of Mona's study at the April Roundtable was consulted FAA Volpe, but the report was not thoroughly peer-reviewed prior to publishing. Per the journal process, the paper was peer-reviewed. On the other hand, please share if Mona as an ascent project gave FAA the opportunity to review and provide feedback before its publication or not. Number 2, SFO used AEDT to decide which GBAS procedure to develop and plans to average GBAS versus non-GBAS noise events to determine whether GBAS created more noise. The Mona team used a different methodology that compares flight by flight, then calculated averages of the differences for each aircraft type using thousands of noise events. Question, Dr. Alonso, why did Mona choose the flight by flight comparison methodology, and could the same methodology be used to compare noise of GBAS to non-GBAS flights for the same carriers and aircraft types? Number 3, at the recent NoiseCon conference session on noise policy review, the FAA was interested in additional data to supplement the NES study, especially for next-gen communities away from the airport. SFO was not part of this NES study. The Mona study used SFO noise monitoring data. Given the SFO noise office has sizable workload and receives numerous requests, a question to Bert is, can SFO authorize Mona to provide the noise monitoring data to SFO? Question to Dr. Alonso, with SFO's authorization, would Mona be willing to do this? This would be a win-win. It saves SFO time and the FAA gets data from that truly represents the actual experience of impacted communities away from the airport for the noise policy review considerations. Thank you.
Thank you for the questions. Let's go 1, 2, 3, and I think Bird, you had part of 3. So question number 1, I think when we made the presentation to the roundtable, I forget the name of the gentleman from HMMH, but he did say to me, yeah, I think we misrepresented what was in that slide. Obviously, the journal review process is a blind review process that we have nothing to do with, and the paper went through all of that. And as Tom mentioned, the FAA and our program manager was working side by side with us through the development of the entire study, had a chance to weigh in, ask for lots of good questions that led to improvements in our methodology, and they had a chance to comment on the actual manuscript before we submitted it to the journal. So,
Provided us with very useful data that maps
right.
aircraft IDs with the engine types and the way they should be run in ADT.
So I would characterize the study and what we've done in London as a partnership with at least some elements of the FAA who've been working with us. So it's question number 2 was the GBAS study, different aircraft cohorts. I mean, we could certainly, if we could identify the GBAS flight trajectories, and I'm not quite sure we can do that a posteriori, we could certainly do comparative studies. Like I said before, we can slice and dice the data by airplane type, by day of the week, by whatever it is, temperature in the atmosphere, et cetera, et cetera. We can certainly do this, I imagine. We have something to
Yeah,
add?
I think there are 2 things that I'd like to say. One is that we chose the routes over which aircraft fly, that we do the measurements very carefully. There are so many variables in what goes on in the Bay Area. You saw that flight profile or diagram that Juan showed earlier. And so by using the surfer route that comes over side-by, those planes fly basically the same altitudes, the same speed, they've got to go through the same waypoint. And similarly for those coming into 28 left and 28 right. That reduces a lot of variability than if we measured every aircraft that was flying around at different altitudes and different velocities and that sort of thing. So we were trying to control a number of the flight parameters so that we could tell better what AEDT was doing correctly and not correctly.
It's like filtering the chaos.
Right, yeah. The other thing is that Bert, in measuring the GBAS flights, had several sound monitors along the path that were measuring point to point to point what the noise levels were. And one of them did come over side-by. And so we looked at that data, but we did not have the other data. And so we did not do a detailed study of the GBAS.
But going forward, would that be something that you could input data that once we know what the GBAS, to be able to see if GBAS is effective at lowering that overall dB?
In principle, yes, the limitation is people. We have a small group and we're really flat out. I'm a volunteer, Don is a volunteer. And
Also data, how many of those GMAS flights were there? In total? I just want
I
to.
forget the number, but it was,
10 to 20.
Yeah,
isn't
this-
it?
Yeah, it's
we were
not
sub
hundreds
20.
of thousands.
I think it was 13 or 15.
So you could have some indication, but you're not going to have, I would say, the conclusiveness of the results we're presenting, or yeah.
But moving,
Yeah.
I understood the question,
Yeah.
and I'm maybe misremembering it.
Yeah.
I think the question was asking that not that necessarily that the Moana project go do this work, but that the methodology of looking at things on a one-by-one basis versus lumping everything together or averaging it. I think that was the nature of the question, but I'm not
Okay.
100% sure.
Yeah, I may have misunderstood the question, but yeah, I would say methodology. I mean, we're comparing reality versus prediction, and it'd be interesting to look at that.
Every aircraft type is different.
Yeah.
And if we mush it all together, we can't tell what works and what doesn't work properly. And so by separating out the 747-400s and the 747-800s and the EL 175s and so on, we can tell better where the program works and where it doesn't work, and try to deduce from that what's going on. So that's the reason for having as much data as we have, so that we can slice it and dice it in various ways to really understand what's happening in the data set.
And you remind me of something. I'll make this comment. ADP has a noise model, but that noise model is informed by data that comes from the certification from the manufacturers, right? The noise model is not perfect. We've established that it has some shortcomings, but you could also argue that noise model could be improved by changing the data that comes from the manufacturers as well. So this is something that could be looked at. Question number 3 was about Bert's data. I would say, I'm gonna let him answer because it's his data and we're just using it. But we're incredibly lucky to have partners at SFO who've actually shared this data with us and supported our study, because without their data, we'll have to rely on the small number of noise monitoring stations that we've deployed, 3, 4, right? And we would not be able to be in some of the locations which make a tremendous amount of sense, as Tom was saying, in order to get, some of the high quality data that's needed for these comparisons. So we have it, it's in the database,
right.
Don, we could share it, I suppose, but.
Right, but it's Bert's decision and that's.
Yes, exactly. So,
Well, I
We can't
mean,
give it out without the permission.
yes.
right. So, and unfortunately, with the way the FAA has approved us to operate, we can't.
And then that's the answer.
So right now, no.
One other set of kudos for Bert, is he has put one of his noise monitors right next to the monitor in my backyard under side-by, so that we can compare.
This close.
Yeah.
We can compare the sound level, and they're right on. So we really try to cross correlate or try cross
And Bert's noise
calibrate.
monitors are you know, $40,000-$50,000 instruments, I imagine. No, it's
Oh,
also
the portables are
cheaper.
30.
Yeah, okay, 30, we're putting monitors that are about $1,000, and we really wanted to know if the quality of those nose monitors was sufficient. And by co-locating these two, Tom was able to look exactly at a much more professional and expensive instrument and know that there were virtually no differences between the two. So,
That we calibrate annually, et cetera, et cetera. Yeah, I was amazed too.
so I think those were the three questions, if I remember.
Let me add my thanks to Bert and SFO for your collaboration and making that data
Oh,
available.
definitely. I mean, we do what we can, and unfortunately, we have a little bit of restrictions. We had to work through the FAA to get permission to do this with them, but, yeah, we're glad to do it.
Thank you. Next, Diane, who we have?
Those are the questions.
Have Mary Jo Fremont. Ms. Fremont, you have 2 minutes.
Thank you. So quick correction, stopjet noise does not allow you to report multiple times the same flight in the same day. If you hit the button again, stopjet noise will erase the previous recording, so there is no duplicate.
I agree with that. That was my impression.
Yeah, let me comment now on what we learned from the MONA study, which was excellent, by the way. SFO uses ADT to decide which GBAS procedures to develop. As Mona showed, ADT noise estimate can be underestimated by several dBs. You only saw today the Foster City monitor, there were others. This means that GBAS noise estimates are likely underestimated and that the GBAS noise estimate used in the SFO decisions may have been overly optimistic. Therefore, we need to be extra thorough when we compare the actual noise caused by GBAS procedures versus non-GBAS procedures. We can't just use averages. We must compare flight by flight. GBAS flights for a given approach will be at best in the hundreds per year, and I'm really optimistic here. Averaging can mask things and may not help you understand what's happening. The core issue is how many loud aircraft occur over various communities and how loud each event is. You do not hear the average aircraft noise, nor are you bothered by the non-loud events. So SFO team, please use the same flight comparison methodology as Mona did to evaluate the actual noise of GBAS flights versus non-GBAS flights and determine whether GBAS flights are less or more noisy. SFO said that they would remove GBAS procedures that are noisier. To make that decision, you want good, solid data, not just averages that can mask reality. Thank you.
Thank you, Ms. Fremont. Next, Diane.
We have Mr. Joseph Check.
Hi, can you hear me?
Yes.
Yes, hi. Thank you for letting me comment. Thanks, Juan, for the presentation. It's a good deeper dive to what we had back in April, so appreciate that. Want to just mention a couple things. One was, well, first of all, that I'm really looking forward to the departure part of the study because that, in conjunction with the arrivals, will be able to tell the whole story rather than just half the story. So looking forward to that. The second thing was about you're studying single events, which is great. What the airport is using is cumulative annual average day, DNL and CNEL. So there may be some differences there in terms of the under prediction for single events versus how it's doing on a cumulative basis. Yes, if it's all biased towards the low end, then yes, there'll be under prediction for CNEL. But if there's aircraft mix which is dominating the CNEL, like maybe there are more 747s or something, then the change in CNEL, the prediction of CNEL is going to be more accurate. So over cumulative base. So I just wanted to mention that. And thirdly,
Sorry, Joe, can I respond to that maybe?
Go ahead. Yes, sure.
Yeah, thanks for that comment. So two things that I would say to that is, one is we compute single aircraft events, but remember the study covered an entire year. So the DNL calculation is a very natural one, and it represents the exact definition of DNL. So that data, although we didn't talk about it in the presentation, is in the paper, right?
Not the DNL, but to be clear, we
Maybe it's
are
not.
measuring the sound peaks.
Yes,
We're not doing the metric calculation from the sound monitors.
right.
So we're measuring LA max
Yes.
and SEL, which is the integral under
Yes.
under the peak. So converting that to metrics is something that we do, but we did not include that in the paper.
Right.
Understand.
The other
Understand,
thing
yep.
is also, Joe, we've talked ad infinitum within the team as to whether the law of large numbers and the law of averages is going to help, because we heard several things in the early stages of the study from the FAA. It's like, oh yeah, one event at a time, yeah, but when you average over large numbers, you know, when the entirety of the cohort for any one type of airplane is under predicting the actual value of the measured noise, there's no possibility for the average to actually be better.
Right.
So we
Actually,
because we have
actually,
every event, we have the individual flights, the distribution of flights, and of course the averages. So we're a little bit suspect about the comment that, you know, averages will end up doing better in the end. So,
You can't average data that's biased and produce results that are unbiased.
That's right.
It simply.
That may be the situation in other airports, maybe in departures, et cetera, but in arrivals to SFO, we found that that's probably not the case. Sorry,
Yeah,
I
I think
cut you off. You had a third comment, so.
Yeah, no, I was just trying to, well, just, I'll rebut that just a little bit and say that if you have some events which are much higher, like even just a few events which are much higher than the average aircraft event noise level, then that outer aircraft is going to dominate your annual average day DNL or CNL. So that bias does the logarithm, the laws of logarithms and whatnot are dominating and affecting your annual day average, but are not affecting your single event, where those averages you presented there were just arithmetic averages and standard deviations. So
I think Tom may want to have a comment, and if not, I can jump into it. So
We can't get down in the weeds here, but the average, by definition, is the average of the events that are above or below whatever the true value is. If we're finding that AEDT is producing estimates that are systematically below what the sound monitors are measuring, and there's no way to crank that back up, averaging things together. And so if you had the slide that's up here now, everything would be around zero, some of it up, some of it down, and the average may actually come out to zero. This, however, cannot come out to zero because there's a systematic bias aircraft.
I think what Joe is also saying, Joe may be referring to these shaded lines, which is a representative average over all the types of aircraft. We did weight it by the number of events, Joe, in there. So the aircraft that fly over a microphone more often are more heavily represented than the ones that fly fewer times. But I think we could certainly talk about this separately if you want, Joe. I think this is perhaps a detailed discussion that's more for the engineers.
appreciate it. Great. Thank you. And then lastly, I was just talking about the DNL and the NA, the N above calculation. I agree that it could be great for complaints and measurement of complaints or gauging complaints. There's some studies that like Adam Schulten and I from FAA presented at NoiseCon, pointing to the fact that NA really didn't correlate any better with high annoyance than DNL does. So it may do better with complaints for sure. It may correlate better with that, but not with high annoyance. So that we'll see. That was from that paper, and you'll see analyses come out published soon. Thank you.
Thanks, Joe.
I'd just like to make a comment. We'll look forward to the detailed technical reports that were referenced in Mr. Scheck's paper that have not been published for over a year. So we look forward to seeing those reports that are the technical basis for those claims.
Excellent. Thank you.
We have one last speaker, Jennifer. Jennifer, you have 2 minutes.
Good afternoon. I apologize because it's 2 o'clock in the morning where I'm at. So I hope you'll understand that. So I bring a little bit of a different viewpoint on, first, thank you to everyone, the scientists and the Stanford team and SFO and everyone for collaborating. This is really great. I just wanted to mention that the analysis is comparing, monitored sound and the one that was predicted. And besides using the model for prediction, the FAA uses this model because the FAA does not do measurements with noise meters. They use this same software to establish the noise contours that, for example, the airports publish, what's within the 65 DNL zone, et cetera, et cetera. So it's not just to predict, but they're actually using this model to quantify the amount of exposure, noise exposure that a population is being exposed to. And so it's not just let's predict, but it's also let's quantify. Independent of all the different weeds that were discussed, which I am not able to contribute to, I just wanted to point that out. And it is my observation in the last decade of seeing the FAA's policy approach is that they actually, this is all great to have, but they're not looking to quantify it for the public who wants to know whether noise is going to go up or down. And in that respect, it doesn't really, the debate about the metrics or the fidelity of the model, it's getting lost because it's never going to be used as long as this is in a research mode. And so eventually, maybe localities will have to just use real noise monitoring and give people, real life information about noise is this level, so that in the future, if that we should have a problem with noise, it's not just up to complaints, but that there's an objective measurement of whether noise has gone up or down. So it's a little bit of a language issue in that we can talk about predictions and we can talk about comparing. And the people don't want to know how our perceptions have changed. We really want to know what our exposure is and what it might be. So I just wanted to point that out.
Thank you, Ms. Jennifer, and thank you for staying up late for us and joining us. Thank you so much. Any more public comment?
That is it for all public comments.
Okay, so I'm gonna go ahead and close public comment, bring it back here for one more chance. Any questions or comments from the panel here or online, Jean or anyone else who would like to say? Seeing none, I want to thank you so much, all of you. I'm gonna call you by your first name if you don't mind.
Absolutely,
Juan,
please.
Tom, and Donald, thank
Yeah.
you for being here. Really, this was very informative. Obviously, we planned for 45 minutes, but I think this topic was so much information for us to learn and dive deeper into. It was very worth every minute, and I really cannot thank you enough for taking the time and joining us here today. And I know members who are online will share the same sentiment.
Thanks for
Clearly,
inviting us.
you put a spotlight on an issue that we have been discussing at the roundtable for quite some time. And now I think what we have is we have data behind what we were talking about that really elevates the topic to where this noise policy review has to happen, the metrics and what is it that FAA is doing. Again, I can't thank you enough for doing the work and more importantly for being with us here today and sharing the results of your study and the work that you have done.
It's a real pleasure. Thank you for listening. And, anytime that we continue to do studies and there's additional data that you might be interested in, we're your neighbors, so happy to come by and just give a quick presentation.
Well, thank you. I really look forward to hearing your departure noise study and seeing what those results show for what's experienced on the ground. And if you need any help with noise monitor locations, we can make it happen.
Have them all, right? So at least the
Well,
ones
except
that's-
I think you may be talking about a different place.
different-
where you want.
No, he's got them there too.
Yeah.
Well, we've got his, Bert's already helped giving us all that data. so-
Yes,
Good.
portables, permanents, they have it all.
I would only echo those comments. I am very appreciative you took time out of your day and a busy afternoon to come here and share with us. This is critical information, and whether or not the FAA is gonna incorporate it anytime soon, at least for our concerns around SFO, this is very helpful. And I also want to applaud SFO for the cooperative and
100%.
collaborative nature. Bert, please extend our
No doubt.
thanks.
I mean,
So,
it's
appreciate
a
it.
Scientific event.
we're trying to get to the right answer,
Hmm,
and you can't get to the right answer without having the right data. So,
Right.
yeah,
100%.
thank you.
Thank you very much.